Number 4 says determine the following indefinite integrals. Print your answer in each part in the box provided. So the first equation is just a polynomial. So if we were taking the derivative, we would use the power rule. That means when we take the antiderivative, we're just undoing the power rule. So the algorithm that we're going to use, if you have a term that is x to the n, instead of multiplying and then subtracting, we do those opposite steps in reverse order. So I'm going to add 1 to my exponent and then divide by my new exponent. And because it's an indefinite integral, we can't forget the plus c. That's on our penalty section on the final exam. It's major point deduction. So we're going to do this all the way across. So I have negative 4x. It's to the 7th, so I add 1 to get 8 and then divide by 8. Plus 8x to the 6th and then divide by 6 plus 12x plus c. You could technically stop at this answer, but when we put our final answer in, it's just sometimes nice to reduce those coefficients a little bit. So 4 over 8, that's negative 1/2 x to the 8th. 8 over 6 reduces to 4/3 plus 12x plus c. This next one, we have a combination of known derivatives. So you have to recognize a derivative of a function that we know, and then we just state the function that created that particular derivative. There's no algebra that can get you back to this step. So secant squared is the derivative of tangent. So the first term, we're going to get tangent of t, and 1 over t is the derivative of natural log of t, but when we anti-differentiate, we have to put our absolute value bars around the expression. And don't forget the plus c. So this one was just a combination of recognizable known derivatives. The next problem is going to require u substitution. So I kind of can see here, I don't recognize this as a known derivative. It's definitely not something I can rewrite as a power rule because I have this expression trapped in my denominator inside a radical. So a good candidate for my u is going to be everything that's inside the radical. So I'm going to let u be x to the 5th plus 3. Then I'm going to calculate the derivative of that. And the derivative of this is du is 5x to the 4th dx. So now I need to go back to my integral and check to see if all the elements I need in du are here. So I have my x to the 4th and I have my dx. So I've got that part of my du right there. So then what I like to do is I like to solve this expression for what I actually have in my integral. So if I divide both sides by 5, now when I translate my integral to variable u, I can see that this part of the integral gets replaced with du over 5. So my new integral, I've got 1 over the square root of u, and then the x to the 4th dx becomes du over 5. And so I'm going to just push the constant out front. So now you can see how this integral translated into this integral. So now I'm ready to integrate the function, but I think that if I rewrite this one more time, I can actually make it a power rule problem, so it's a little bit easier for me to work out. So this will be the same thing as 1/5 times the integral of u to the negative 1/2 du. So the antiderivative is 1/2 u to the positive 1/2, and when you divide by 1/2, that is the same thing as multiplying times its reciprocal. And so my final answer is 2/5 u to the 1/2 plus c. But my original integral was in variable x. So for indefinite integrals, we have to take it back to the original variable. So my final answer in my box is 2/5 x to the 5th plus 3 raised to the 1/2 plus c. You could also write it in radical form. That would be okay too. These are equivalent answers, but there's no reason to go back to that. We're perfectly capable of reading that just fine.